Hi everyone, I'm Simon, and I'm part of Group 6 along with Ryan and Mu Wei, and we're going to be talking about Pushdown Automata. So let's get started. So far in this course, we've looked at two main extremes of constructions for computing things. We've looked at finite automata, which, as we know, they perform exactly one operation for every single input symbol. So say your input is AABB. Every time you see an input symbol, you do one transition in your state space, and then you move on to the next symbol. And then the next symbol, you do another transition, move on to the next symbol. Every symbol corresponds to exactly one transitions. And then once you get to the end, you've got no more symbols left. That's it. You're done. If you're in file state, you accept. So Turing machines are a little bit different, as we know. They're kind of at the opposite end of the spectrum, and they can do as many operations as they want. So say we've got the same string, A, A, B, B. We can go right and then right again. Maybe we go left. Maybe we make the A big A, and then we go left again, all changing our state space and everything all at the same time. And the outcome of this is that they can be divergent, which is a little unfortunate because sometimes you just won't get an answer for what you're trying to compute. So what if we want the extra power that comes with being able to operate on each symbol multiple times, but reduce the risk of divergence? We want to try and minimize getting lost in infinite loops. So we introduce pushdown automata, which is like a Turing machine, except instead of having a tape, we have a stack. So I think we all know what a stack is, but just in case you're not sure, it basically is a first in, last out kind of system. So it's like stacking plates, which is why people talk about it like that. You put an object on the bottom, say hashtag, you put something else on top, and if you want to get to the hashtag, you have to get rid of the A first. You can only access and put things onto the top. We say pushing onto the top, so that's a push, and then if we take something off the top, that's a pop. So we access the top. Notice if it were a queue, we could just endlessly loop through the information in the queue, but with a stack, you can't do that because if you want to get to the bottom, you have to sacrifice information because there's nowhere else to store it. The other noteworthy thing of pushdown automata is that this input tape up here, it still only moves right. So once you've read an input symbol, that's the only time you read the input symbol. So you can put it onto the stack, but if you don't put it onto the stack, the only way you can know what symbol you've had is if you stored it in your state space in some way. Anyway, I'd also like to make the note that non-deterministic pushdown automata recognize different languages from deterministic automata. This should be the normal way of thinking of things, but from the two examples we've seen so far, that's not the case, and those are the exceptions, and pushdown automata aren't. So in this talk, we're focusing on non-deterministic pushdown automata because they're just a bit more powerful and interesting and kind of cool. But yeah, every time I say pushdown automata, I mean non-deterministic. Okay, so formally speaking, we define a pushdown automata as a six tuple. It's very similar to a Turing machine. We've got a state set. We all know how that works. Input alphabet, sigma, which is, alphabet language of our strings. And then we've got gamma, which instead of being a tape alphabet is now a stack alphabet. So you can have extra symbols on the stack if you want, whatever you like. Now, our transition function is slightly different. This little epsilon down here in every single, in the sigma and the gamma, basically just means that we accept epsilon transitions. So either we read an input symbol, or maybe we don't. We read something from our stack, we pop off the stack, or maybe we don't. And then we take a current state, and then we push something onto the stack, or we don't, and then we go to a new state. Very straightforward. Okay, now Q0 is our start state, you know how that works, and F is the set of final states as like a subset of Q, which I think we're all familiar with. So obviously that makes a language the set of strings that has at least one computation that ends in an accept state. So because you only read each input symbol once, you don't have to explicitly go to a halt state at all. You're just either in a halt, in an accept state or a reject state because you halt once you've read every input symbol because you only read them once. And you've finished all of your stack operations or whatever. Okay, so as long as one computation ends in an accept state as well. Just one because it's non-deterministic, so there could be multiple possible computations. Okay, so just going through an example. This language here is very clearly one of the non-regular languages, classic example. And we're going to show that pushdown automata can recognize it and decide it and so on. Okay, so I think the idea here is pretty clear. Every time we read a zero, we want to push something onto the stack, and then when we start reading ones, we want to pop off the stack and make sure we've popped off the same amount of things as we pushed on. Formally speaking, there's no real way to recognize the bottom of the stack. So we can just have our start state here, and we can just put a little, like before the start transition. So we'll say epsilon, read nothing from the input, read nothing from the stack, and then we're going to put, say, a $sign on the stack to mark the bottom, which is just one option. You can put any symbol you want as long as it's specifically that this is the bottom of the stack. Okay, then we're going to go into the second state here, and we can do, how about we just say every time we read a 0, we don't read anything from the stack. We don't care what's on the stack, but we're going to push, say, a hashtag to the stack. So for every 0, we put a hashtag onto the stack. And then when we start counting ones, we're going to want to read a 1. We're going to want to pop a hashtag off the stack. So we'll read the hashtag from the stack, and then we will put nothing back. And just to be clear on this little notation here, this here is sigma epsilon, this here is gamma epsilon, and this here is gamma epsilon as well. Okay, and then we don't know how many ones we're going to have, so we'll just do that same transition again as many times as we need. Okay, and then in order to get to a final state, we're going to make sure that we have no symbols left to read. So we're going to read a blank, and we're going to make sure that we're at the bottom of the stack. So we're going to want to read a dollar from the stack. And then it doesn't really matter what we push onto the stack. We can put anything we want, but that's fine. Okay, so this seems like a pretty decent construction. How about we step through an example? So say we have the string 0, 0, 1, 1. We're going to start in our start state here. And our input is going to be our you could say tape head, but it's not really a tape, is looking at this first 0. And I'm going to do an epsilon epsilon transition, so not do anything, but we're going to put a dollar onto the bottom of our stack. So this down here is going to be our stack now. Okay, now we're in this state, and we're going to read a couple of zeros. So we read this first 0, we read an epsilon, and we push a hashtag onto the stack. And now we've moved on to the next 0 with one symbol across. And we can't go back again. We only read each input symbol once. Okay, then we do the same transition again, very simple. Move forward 1, put another hashtag on the stack. And then our next transition, well, now we can read a 1. We have to read a 1, it's the only option. So we read this 1, we read a hashtag, so let's read that 1, move this forward, read this hashtag, and then we're going to put nothing onto the stack. So we're not putting the hashtag back, so there's one less hashtag. Now we're in this this next state here. We can do the same transition again. We can read the 1, move forward, read the hashtag, put nothing back, and then we're like, oh, okay, we've got a blank, we've got a dollar sign on the bottom, we're going to put nothing back, we're just going to move to this state, nothing needs to change up here, not at all, and then we accept the string because we're in an accept state. Beautiful. Okay, so next we're going to talk about a thing called context-free grammars. So a context-free grammar is a set of substitution rules with variables and terminals. So we've got an example grammar here, G, which is given by A goes to 0A1 and A goes to epsilon. So here A is a variable. It's the only variable in this grammar. You can have multiple variables. You could have a B. Normally you write them as capitals. And also on the top left, we call that the start variable. Get to that in a second. And then we have 0 and 1 being the terminals. So the reason they're called terminals is that as you're doing your substitutions, you could be introducing new variables. But once you only have terminals left, then you're finished, you can't substitute anything, and you say, this is a string that's part of this grammar. This grammar makes this string. Awesome. So let's just step through an example here. We're going to start with our start variable A, and let's say we do the first substitution. We'll go 0, A, 1. Okay, now we have another A in there, so we could substitute again. So we're going to have our 0 and 1 on the edges, and we'll turn this middle A into another 0, A, 1. And maybe we think, okay, I think I'm done now. We'll make the A an epsilon. Let's have a bit of variety. So we have 0, 0, epsilon, 1, 1. Of course, we all know epsilon means nothing. So we can do 0, 0, 1, 1. And then we say this string is part of our grammar. Generally speaking, or formally speaking, really, the language of a context-free grammar is a set of strings that you can generate by applying these substitutions. Sometimes call them context-free languages. That is terminology we'll use. The language is context-free if it's generated by a context-free grammar, stuff like that. So in this case, 0, 0, 1, 1 is an element of the language of G. And I think it's pretty clear to see here that I've specifically chosen G so that it's 0 to the n, 1 to the n, an element of natural. Because every time you introduce a 0, you have to introduce a corresponding 1 on the right. And the only way to get rid of all the variables is to not add anything in the middle. It's pretty clear construction. So you may be wondering, these examples are a bit suspicious. Why are you suddenly talking about context-free grammars? Well, that's a major theorem. Non-deterministic pushdown automatas recognize exactly the set of context-free grammars. So, of course, that can be split into two lemmas. First off, if a language is context-free, then there exists some pushdown automata that recognizes it. And if a pushdown automata recognizes some language, then it must be context-free. Awesome. So we're going to have my other group members take you through those two lemmas. First up is Ryan with lemma 1, and then Mu Wei on lemma 2. So take it away, Ryan.
Thank you, Simon. The forward direction of the lemma states that if a language is context-free, then there exists some pushdown automaton that recognizes the language. So our idea for this proof is that for some context-free language A, we know that there has to be a context-free grammar that generates it. Our goal is to construct a pushdown automaton P that is equivalent to G. So let's say pushdown automaton P takes in the input string W. It will now determine if there's a possible derivation for W using the context-free grammar G. So what we do is we first push the start variable of G, go through the set of required substitutions, and finally try to end up with the exact same string on the stack. And then we individually read in the input symbols and match it with the stack and pop them as we go. Finally, if we reach the end of the input string and we reach an empty stack, we accept the string. The stack being empty will be denoted by a character. In this case, it is the $, and similar to how Simon did it. And we push this before pushing the start variable. So this is how it would look. So we finally, after all the substitutions, get the string onto the stack, followed by the symbol that denotes the empty stack, and then read in each input symbol and pop them as we go. And finally, when we reach the end and have an empty stack symbol, that means we accept the state. Now, how would we do a substitution on the top of the stack? Our idea is to go backwards. So let's say we have the substitution A gives A plus B. So we first replace A with B, push plus, push A. So like in the stack, we would replace A with B, push the plus, push A. Now we can formally represent it like this. So on reading the symbol A, we replace S with X, Y, Z. And internally, there are two states that aren't shown in the shorthand notation. So we would replace S with Z, push Y, push X. Now we quickly run into a few issues. First is, how do we select the correct substitution for a variable? This is where non-determinism comes into play. We non-deterministically select a possible substitution for the start and any variable at the top of the stack. The next issue is, how do we store intermediate strings? Because there are many strings which will have variables in the middle, and we only have access to the top. Also, if there's a terminal symbol on the top of the stack, what do we do with that? Our solution is to store a part of the string. So if there's a start variable on the top, we non-deterministically select a possible substitution. If there is a terminal symbol on the top, then we match it with an input symbol and pop, and we move on to the next input symbol and the next symbol on the stack. And we repeat this process until we reach the end of the input and we have an empty stack. When we reach this particular situation, then we accept. So this diagram should explain it. So we initially have A as an input symbol, and we have A on the top of the stack. Then we match them. So we pop A and move to the next symbol. And so now we have the plus and plus on the top of the stack as input symbol. And now we repeat this process. And if there's a variable on top, we go through a substitution. Now, this is the final high-level description of the entire construction. So we first push the $sign on top of the stack to signify when the stack's empty, push the start variable, and then follow these steps. If there's a variable on the top, non-deterministically select a possible substitution. If there's a terminal symbol, we match it with the input symbol. And if they are the same, pop. If they are different, reject that branch of the computation. Finally, if we reach the end of the string and input string and we have an empty stack, then we accept. And with that, I conclude my side of the proof. And now I'd like to pass it on to Mu Wei.
Now we prove the reverse direction of the theorem, which is if a pushdown automata recognizes some language, then it is context-free. Here's our proof idea. What we want to do is, given any pushdown automaton P, we try to construct a context-free grammar G that generate the language of P. There are 3 steps in the proof. First, we modify P to simplify the task. Second, we construct G to simulate the computations of P. Third, we verify the construction of G. So what exactly should we do to modify the pushdown automata? First, it should only have single accept state. We can do this by adding an epsilon transition from each of the original accept states to the new accept state. Second, stack is empty before accepting. This can be done by pushing a special character, let's say $, to signify the empty stack and the start state. And at the accept state, we keep popping out all symbols except for the special character. And then after that, we pop the special character like signify the empty stack to the new final state here. Note that after this modification, the language of P remain the same. And the third is each transitions either push a symbol onto the stack or pop one of the stack, but not both. So for the transition, which push and pop at the same time, we can split it into two transitions. At first, push a symbol and then pop a symbol. And for those who doesn't push or pop, we can simulate it by pushing and dummy symbol and then popping the dummy symbol immediately after it. After modifying the pushdown automata, we can now construct the context-free grammar. Our strategy is to create a variable for each pair of the states in the pushdown automata to simulate its computation. Here's an example. Suppose there's two states, P and Q, in the pushdown automata. We create a variable, APQ, which is capable of generating the same set of strings that takes the pushdown automata from state P to Q, starting and ending with an empty stack, which means the stack is unchanged after the computation. And because we modify the pushdown automata, there's only two possibilities during this computation. Please look at the figure here. The x-axis represents the input string, and the y-axis represents stack height. So you can see at the start at the beginning, the stack is empty, and during the computation, the stack is not empty. So suppose there's a transition from state P to Q by reading input A and push something into the stack, and another transition from state S to Q by reading some input B and popping some symbol out of the stack. We can write a rule for APQ that derives the symbol A and the variable ARS followed by the terminal symbol B. And the other case is that the stack is empty during the computation. Let's say the stack is empty at state R, then we can derive the rule APQ derive APR and ARQ. APR means the set of string that can take from state P to R, and ARQ means the set of string that can take state R to Q. And finally, we also add a rule APP derive epsilon, because for any pushdown automata, it can stay at the state without reading anything. To finish the proof, we have to verify the context-free grammar we generated. So we have to prove APQ generate X if and only if X can bring the pushdown automata from state P with an empty stack to state Q with an empty stack. I'm just gonna give a sketch of the proof because there's a if and only if in this statement. So it also have two directions. For the forward direction, if APQ generate X, then X can bring P from state P to state Q. We can prove this by induction on the number of steps in the derivation of X from APQ. And here's a detail of the proof. Basically, we just use the three rule we construct before to prove it. And for the reverse direction, if X can bring the pushdown automata from state P to state Q, then the variable APQ must generate the string X. This is also proved by induction, but on the number of steps in the computation of P that goes from state P to Q on the input X. And here's a detail of the proof. And now we complete the proof of the reverse direction of the lemma.